Find the point on a particular line that's closest to another point. So, all right, let's see. Y equals 5x minus 1, y-intercept of -1, slope of 5. I'm not going to be overly careful about this, but slope of 5 is pretty steep, so maybe something like that. There's my line 5x minus 1, -3, 8. We'll arbitrarily put 8 right there. So -3, 8, it's about here. When we talk about a distance from a point to a line, I'm talking the perpendicular distance, the shortest distance that I can get. So hopefully that's perpendicular-ish, so that I make a nice right angle there. I'm looking for the point on the line where that happens. So I'm looking for this point on my line. Let's see, closest. If we say closest, we're talking about distance. There's a formula for that. The distance formula you may remember from your past. Big square root, difference of the x's squared plus difference of the y's squared comes from the Pythagorean theorem. Oh, that's a 1. There's the distance. So I want to minimize the distance. Well, I certainly can't do it like that. We need some specifics here. My point, I'm going to call the point x2, y2 is -3, 8. And x1, y1, I'm going to call the point on the line. Well, I don't know what it is, obviously. I'm looking for it. But I can say that it has some x coordinate, and since it's a point on the line, its y coordinate comes from the line, the equation of the line. So here's my point number 2. Here's my point number 1. Let's fill into the distance formula. Big square root. Let's see. x2 we're calling just -3. Minus x squared plus y2 minus y1 squared. And we can clean that up a little bit. Let's see, this is -5x, and we got 8 minus -1. Sounds like 9 to me. And let's go ahead and square them out. We are going to have to take a derivative eventually, so whatever we can do to make that easier is a good idea. I'm going to go ahead and square. And we'll square this one. 25x squared. 2 times 5 is 10 times 9 is 90. 81, and there we go. And still going. Let's combine some like terms here. So I have 26x squared, and looks like minus 84x plus 90. Whew, okay, so there's my distance. Find the point on the line that's closest. So now that I have the distance, we're going to need to take a derivative of that distance function. Oh, that'll be fun. It's a giant square root. So let's see. Derivative of a square root is 1/2 times the square root to the -1/2. Like that. Times the derivative of what's underneath. There's my derivative. Looking for critical numbers, so I need to know where is that equal to 0. Well, it's equal to 0 where its numerator is 0. And that happens when x is, this is a fun number, 21 over 13. So we're just adding 84, dividing by 52, and then simplifying. Y, since we're looking for a point, we're going to need the y coordinate too, but y, this is a point on the line, so y equals 5x minus 1. And for y, we get 92 over 13. So my point on the line, 21/13, 92/13. And if we think about this, 21/13 is somewhere between 1 and 2, a little closer to 2 than it is to 1. 92/13 is somewhere between 5 and 10. There's my point. This might be one, I don't know that I want to take a second derivative of that, so I'm just going to use the first derivative to make sure that we've actually found a minimum of the distance. So let's see. For points to the left of this point that we found, values of x to the left, I'm going to use 0. I get 0 minus 84 is negative. So negative to the left, which means my function, my distance function is decreasing to the left of this point. And then I'm going to try something to the right. So I'm going to try like x equals 10, which I am certain is to the, or no, I don't have to do that. I'm going to try x equals 2, which I'm certain is to the right of this point. And if I do that, 52 times 2 minus 84, I don't know what that is, but it's definitely positive because 52 times 2 is more than 100. So increasing to the right, which means that point is indeed a minimum, which is what we're looking for.